my name's Alison. I'm a software engineer at Kry10. I'm not sure why I need to look at the slides for that. So I'm going to be talking about supporting container images on seL4 using Kry10 OS, which is what we're developing. Okay, so I hate definition slides, but I kind of need to do it because I think everyone in this here today would probably have a different thought about what it means, what a container means. And so for this presentation, I'm splitting it up. I'm splitting up the definition into three areas. That is, containers can be thought of through a lens of a build system, can be thought as a packaging system, or it could be thought as a OS virtualization mechanism. Okay, and so to map these definitions out, it's good to look at it in the form of the life cycle of a container. And you have various operations you can do. But yeah, you can build it, you can push it somewhere, or so you can run it, you can push it up to a registry, you can pull that down, you can scan it for doing SBOM attestations, and you can sign it and push it back up. So there's a lot of stuff you can do. So let's look at it in the form of sorry, Siri just went off. So, let's look at the form of a build system. So it's a mechanism for assembling images with their build and runtime dependencies. And so it can take a Docker file or a build pack or whatever container building infrastructure you're using, and it spits out a tarball of artifacts that represents your image. And so the good thing about that is it kind of unifies various dev cycles into a single tool in terms of pulling things down, invoking your compilers, and packaging it up and with their runtime dependencies. So then there's as a packaging system, so it's a mechanism to push and pull images across local remote development and in production environments. And that's obviously great because you get versioning, tagging, image reuse, caching. And you also get some other cool stuff like being able to do a software bill of materials scan and signing that so you can have vendor specific. So you can trust that image itself. And then lastly, there's an OS virtualization component to it. And so it's a mechanism that bundles in applications, its configurations and libraries dependencies into an isolated namespace and keeping it independent from other environments running in parallel. There is the benefit. Why would you do that? There are some security benefits. It's not perfect. Definitely not talking about it at the seL4 conference, but there are some benefits there. But I think it's really good because it gives you a lift and shift approach to development. You can take an application and push it across different environments. Okay, so I only have 15 minutes, so I'm only going to focus on these specific parts of the container lifecycle. Okay, so why am I speaking about this? So what are some current frictions with seL4 approaches? So to do that, we can look at some of the approaches that currently exist. We've got CamQ's CMake, we've got microkit BYO build systems, you can do development in Docker shells, or you can use Nix. There are challenges with that. There's challenges managing different tooling prerequisites. It's common to have to battle with that. When I was a thesis student, I think it was a running joke that the first semester was spent learning how to build seL4. And so, it can be challenging. And it can be fragile, and you have to hope you're not using a version of Ubuntu from 4 years ago. So builds, the next one is builds exist within the context of a full source tree. So you often, with at least CamQ's, you have to pull in the full source tree for your build. You have to battle the CMake build system and its meta programming language. And then across all the different versions, across CamQ's, microkit, Docker shells, Nix, they all differ. They all significantly differ, and it's hard to transfer across different tooling. In terms of packaging, there's not really much packaging solutions available. You can pass around source trees, but then you go back to having to battle. It can be annoying to have to battle with tooling prerequisites. You can pass around binaries, but that doesn't really capture the runtime dependencies. So it doesn't really exist And then as an OS virtualization mechanism, you can run things in VMMs. So there's the CamKeys VMM and the MicroKit VMM. Crafting your own custom VM can be quite daunting. It's quite powerful to be able to build your own VMM as a library, but some people just want to run an app or two. And so it's a lot of overhead, and then it's slow because you have to build your own rootfs, and that's error prone, and you have to keep reiterating. Why am I doing this at Kry10? So we have a couple of values in Maori. I'm not going to try to pronounce it because whilst I'm being recorded, but do not, the value is that I'm resonating here is we don't want to waste the feathers of the bird. And that essentially, that essentially means we want to ensure that our people have the right tools for the job, and we don't want to waste resources that are in front of us. Containers is a pretty well specified standard. It's battle tested. It's production. It's the world's cloud infrastructure uses it. And so yeah, it's a great ecosystem that we can piggyback on and use to solve some of these problems. So a quick intermission. I'll show you what does it mean to actually use all these things in an seL4-based operating system before I go into the technicals. Sorry, give me a moment. Just run the system. Should have done that. Okay, so I have a pretty standard system that you can get if you check out our evaluation license. I could have a pretty simple hello C app. It's quite arbitrary. It prints a bunch of arguments. It prints a bunch of files, and then exits. And then my Docker file can just be a build of that application. I can build up a file system of those two files that it wants to print, set up some environment variables. And so I can compile that, and it's running. And I can see it now uploaded to my system. Can do that for Elixir Mix as well, a bit more of an involved system where we have to do some dependency building, compiling, and again, we set up an Elixir app. And cool. It is run. It should be running. Cool, and it's running. I can stitch this all together, and I could build a compose file. I could have two apps. I could have a server and a client, and the client depends on the server. And the two apps will communicate over a shared network, which is going to be back here. And I can run that, and I'll have the set of servers there. And then I can do a compose down and tear that down, and those servers are gone. And as a packaging solution, I could have an MQTT broker, which I'm using NanoMQ here. It builds the broker. It comes with a config file that I want to distribute the app with. And so I build it. That broker's now running, which is great. But I push that image somewhere. It's a package that other people can pull down. So I've just created another Docker file that pulls down this image and modifies the config a bit. And then I push it back up, and now I'm running two MQTT brokers, each with a different port on a different port. Yeah, so that's the package management approach. It's quite. Probably someone's thinking that I must have been born yesterday. All I'm doing is demonstrating how Docker files work. But I think that's exactly the point, because I want to be able to use these solutions on seL4. And the last one is I can run a micro VM. So we have a fallback. If you can't run the application on our own operating system, you can throw it in a micro VM. And this example is just a Python app, a Flask app that I want to distribute and just play it on a VM. I'm going to run on seL4. That's going to take a little bit more longer to compile, so I'm just going to move on because I think I'm running out of time. Okay, I had some fallbacks. Okay, So building and running a container. So going back to the life cycle, you can split it up into, I'm splitting it up into two problems, building and running. So when you run it on Linux, or just a regular container build, you build up the Docker file and all the layers of that image, and that will spit you out an OCI tarball with the blobs that make up those layers and a config of how to run it. The challenges here is, if we want to take this approach, we ideally don't want to really interfere with the user's builds. They want to be able to write their Docker file how they see fit. And in the packaging, there's all these runtime dependencies we need to capture, and we want to capture the root FS and the environment variables, and make that available when we want to transpose that to seL4. So yeah, and then continue on an example when you actually when it's time to run the container, it unpacks the archive, and then it calls runc usually, which is just a true root with extra steps, and then you're running your program. Challenges here is ensuring that run state can be appropriately unraveled and loaded when executing the image. And also, if we want to bring this to seL4, it's quite simple in terms of running it in a VM. We don't have to do much. It's already kind of a root file system, but we still want to be able to inject our own runtime functionality to make apps work with others in the system, because we want micro VMs to be a first-class citizen. So rewinding. Oh, sorry. Okay, and so building container, what we have is a tool called CostKit, nothing to do with MicroKit, lots to do with BuildKit, which is Docker's build engine, which can consume Docker files and spit you out tarballs, spit you out OCI archives. What this gives us is an ability to control the lower level build of a Docker build, and we can then copy the root FS artifacts and export it. And what we end up doing is we transpose a bunch of configuration state into that OCI image that helps us decode it when it's time to run it, such as what pages it requires, what's its scheduling priority, how it needs to communicate with the system. So we transport that, capturing runtime. So we inject seL4-specific configuration under namespaced attributes. And when it comes time to actually run it, we can produce out some binaries of its entry point, its root FS, and a bunch of capabilities that it needs when it needs to be loaded, similar to how CapDL would work. And in the micro VM case, that also comes with a VMM and our own injected init task with the container's root FS. Sorry. Okay, and then on running a container, that image gets sent to our root server, which performs all the loading. It comes with the init ID and the elf file. There we have a dynamic process in our libc that will bootstrap and install the root file system, and make those files available to the app. So then zooming out, you can have a micro VM, and we also have our own init task with vSocket ports that expose it to the outside world to communicate with other apps. And stitching it together with composed systems, we can also do the exact same principles as what Ehil was describing with an untyped pool, and we can bring up the client and the server, and the network is going to operate, and then when it's time to take it down, we can compose down. I'll finish there, sorry. Yep.